Okay, so today we're going to discuss plate tectonics, and we're going to kind of sum up everything that we've learned so far. Today we're looking at the history, and then tomorrow we're going to look more at, or sorry, the next time we meet, we're going to be looking at more of the types of boundaries there are. Okay, so I do apologize if my little head over in the corner here gets in the way. I'll try to slide it out of the way as best I can. So some background information looking at the history. Okay, so up until 1880, the Earth's surface was considered to have been the same since it was created. Okay, so they didn't realize that all the continents moved. They didn't know what caused things like earthquakes and what caused things like volcanoes to form. They just thought that they were always there, and these were occurrences that just happened. So now they are starting, after 1880, they started to really think about this a little bit more. So this was associated with the idea that the Earth was flat and that the sun and stars revolved around the Earth. There's still some people that still believe that it's flat. I'm not quite sure why, but some people do. But it's not flat. It is definitely a sphere. So by the 1900s, says the evidence was found that the continents were moving. So if you look here, this is very similar to the project that we just did. It says fossils of the same organisms found on different continents. So you can see how the different continents matched up. Okay, the South America, it kind of fits like a puzzle, but also if you looked, there are the same fossils in this location as there are in this location in Africa. Okay, and because they are the same in those two locations, it shows that the continents had to be together. These are animal fossils and plant fossils that could not have traveled across a great ocean. Okay, same with down here. Okay, you can see, and all throughout here, there's this pattern of fossils being found in similar regions, but on different continents. Seafloor spreading, it says, shows similarities either side of a mid-ocean ridge. Oops, let me go back. So you can see here, right in the middle of our ocean, okay, this is, again, South America and Africa. There is a ridge, okay? It's like almost like a, not a trench, but an area where we can definitely see that there's a lot of volcanic activity, a lot of lava flow and stuff like that. So right in the middle, we can see that the rock on either side, equal distances from each other, are very similar. They have the same types of rock formation. They also have the same direction of iron. Okay, Earth is one big magnet, and they find that over millions of years, that magnetic field swaps. So sometimes it's facing north, sometimes it's facing south, and they find that the rock has similar magnetic properties equal distance from the center point where that ridge is. So that proves to them that as it spreads, a new rock forms, that new rock continues to spread. So it's the same type of rock on either side of that ridge. Okay, and this is years older rock further away, newer rock as it gets closer. So the age of Earth's crust, red is young, blue is old. Okay, so you can see closer to that ridge is the younger rock, okay, or younger crust, and then further away is the older. Okay, same with, it's kind of hard to see in this picture, but this is South America, this is North America here. Okay, so you can see the young rock is right along the edge, old rock or crust is further away from that ridge. Separation of Africa from Saudi Arabia. It says it's causing the formation of Rift Valley. So the same thing that happens in the middle of the ocean where the two continents are pulling apart. Here, we can see this happening in the Red Sea. So it's literally pulling Africa away from the Arabian Peninsula here, or Saudi Arabia, and it's creating the Red Sea, which the Red Sea will eventually be connected into the Mediterranean Sea and the Indian Ocean as it pulls apart. Okay. Also happening down in a lot of these regions. Okay. So Africa will be all split up eventually. This is just an example on land of an area where this is happening, okay, where it's pulling apart. So in 1912, scientist named Alfred Wegener proposed an explanation that the theory of the theory of continental drift. Okay, so he was the first one to think or to come up with the idea that all these continents were once together in one big continent called Pangaea, and then they slowly separated apart. You can kind of see a zoomed in version of that here. Okay, so this was 200 million years ago. In the grand scheme of Earth, that's really not that long ago. 130 million years ago, starts to pull away, 65 million years ago, and then present time. Okay. So there were animals living on each of these lands as they went. Okay. This was only millions of years ago, not billions of years ago. Wegener suggested that at one time, all the continents were joined together in that supercontinent called Pangaea. So again, this is very similar to the picture that you guys created in that simulation the other day. So later it says it was understood that the Earth was made up of distinct slabs of land called plates. So if we zoom in here, you can see there are many different plates. These are just the main plates. Okay, North American plate. Pacific plate, which is in the ocean here. Then we have the Nasia plate, however you say that. South American plate, African plate, Eurasian plate, Indian plate. Okay, so there's all kinds of, all different plates, all split up all over the place. Okay, and each one of these colors, and we did show a picture of this very similar a couple weeks ago. Each one of these colors represent a different type of plate boundary. And we're going to get into more details about those plate boundaries later. Okay, but converging just means that the plates are coming together. Diverging means they're pulling apart. And transform means that they're sliding across. Okay, and then dotted means they're not sure. Scientists aren't sure exactly what's going on in that region. Okay, so you can see all the green here. This is where things are pulling apart and new rock is forming. Same with down here. So a lot of those are found in the ocean. Very few places where they're found actually on land. One of those being Iceland. Okay, Iceland, it shows where there's a divergent plate right across the landmass there. So it was discovered that these plates moved over molten crust. The theory of plate tectonics was developed. Okay, this little video here, for some reason, it's not working, so we're going to skip that. Okay. So now looking at the plates. Okay, again, these are all the plates here. They are kind of split up in chunks. Part of them have oceans. Part of them have continents. Okay, but this is the idea of the way Earth is currently split up into their major plates. So plate movement. So why do they move? Okay, and we talked about this a little bit. You've done a project, or you should have done a project on this, but they move because of convection currents. So the plates move on a bed of molten lava found in the mantle. And we'll kind of see how lava flow. Now, that obviously this isn't in the mantle, but this is how lava kind of flows.
We've touched down on a dry, brittle surface of recently cooled lava. Once the helicopter leaves, we're on our own for a couple of days. This place has no water, no shelter, no life. Except I'm told for a few snakes. But I think it's really going to be worth it. I've come all this way to see one of the most remarkable volcanoes anywhere on the planet. Erta Allen. name means the smoking mountain to the local Afar people. It's reckoned this volcano has been continuously erupting lava for longer than any other on Earth, though no one's quite sure because it's only been properly studied for the last 40 years. I've been lucky to see a lot of volcanoes in my time, and I've never seen one that has a permanent lake of molten lava in its crater. But there's another reason why this volcano is very special. And to see that, I need to get down into the crater and see the lava up close. It's a 30-meter vertical drop to reach a wide terrace below. And the lava lake itself is a little further down. I've waited until sunset to take a closer look because the lava is at its most spectacular at night. This is as close as I can safely get. Oh wow, right. That is magnificent. I mean, it's taken us a hell of a journey to get here. That makes it all worth it. Standing on the edge of an active volcano, right next to a big pool of molten lava. What makes this lava lake more than just pure spectacle is that it's a window that allows us to look deep into the Earth. And it helps us understand the forces that shape our planet. Just take a look at the motion of the lava lake speeded up. Something intriguing is happening. The movement of the lava follows a very distinctive pattern. It wells up on one side of the crater, forms a dark crust as it cools. Then this crust moves across the surface of the lake, driven by the churning action of the lava below. Finally, the crust sinks back down. As we'll discover, this process of molten rock churning away below the surface affects our entire planet. That's because this lava lake is connected to a gigantic source of heat that lies deep inside the Earth. I think it's fair to say that most of us go about our daily lives completely unaware that underneath our feet, our planet is incredibly hot. I mean, we live on a thin skin of cool rock, precariously located between the cold freezing of space up there and a red-hot furnace down there. And what a source of power this furnace is. The Earth's heat does far more than just fuel volcanoes. It created the first atmosphere in the oceans. It continually reshapes the planet's surface, builds great mountain ranges, and moves entire continents. And it created the conditions for life on Earth to begin.
Okay, so you can see, as the lava kind of flows across the the volcano there, it's very similar to the molten rock underneath of us in the mantle. It creates those currents just the same as what you see there. And instead of, obviously it moves a lot slower though, way slower. And the continents that are being moved are way more massive than the dried rock that's on top of the volcano. But you can get the idea. It says the lava causes the mantle above it to expand and move to the surface. So this simulation is going to kind of show, how this works inside the mantle. Obviously sped up quite a bit though.
But the huge molten core contributes something else essential for life on Earth. A way of helping to regulate the planet's temperature. It's a remarkable system. Magma heated by the core rises towards the Earth's surface. As it spreads sideways, the Earth's crust is very slowly dragged apart. This moves the continents, creating the Earth's restless and ever-changing surface.
Okay, so in this video here, you'll see that there is already hot water that is, that was heated from the bottom, and it's causing convection currents. They're going to put blue dye and red dye in. The blue dye they're putting in on the region or in the area where the water is flowing downward, and the red dye is being placed in the area where it is moving upward. You can kind of see as they put these two colors in, you can start to see the convection current that's in that water. So the blue is following the cold water, and then the red is where the hot water is rising, and then when it gets to the other side, it starts to sink, and the two start to eventually mix up, causing it to be a purple color. Okay, so that's where we're going to end off today. So now you have some questions to answer.